So here in this problem we have to find the rate of heat removed from the bread in kilojoule per hour, and we are given that the mass of the bread, it is 350 gram, or we can say that 0.350 gram, and we are given that we have to cool the bread temperature from 30 degrees Celsius to minus 10 degrees Celsius, and the rate, it is given as 1200 loaves per hour, or let me write more correctly, this is 1200 bread per hour. And the temperature of the air, it is given as, this is air, and its temperature, it is given as minus 30 degrees Celsius, and the specific heat of the bread we are given as 2.93 kilojoule per kg degree Celsius, and its latent heat, it is 109.3 kilojoule per kg. So we note here that the cooling rate is 1200 bread per hour, and bread can be considered to flow steadily through cooling section at the mass flow rate, that is the mass flow rate of bread we're going to calculate, and it will be equals to the rate we are given as 1200 bread per hour times the average mass of the bread, that is 0.35 kg per bread. So we're going to solve this and we'll get the value as 420 kg per hour. So this is a mass flow rate. Next we'll be calculating the heat removed from the bread as it is cooled from 30 degrees Celsius to minus 10 degrees Celsius. So here heat will be of two types. The first one is the sensible heat, and next will be the latent heat. So Qs dot, we know it is m dot of bread times C of bread times delta T. So mass we have calculated as 420 kg per hour times Cb we are given as 2.93 kilojoule per kg degree Celsius times delta T, it is 30 degrees Celsius minus 10 degrees Celsius, that is 40 degrees Celsius. So we're going to solve this and we'll get the value as 49,224 kilojoule per hour. So this is sensible heat removed. Next we'll be calculating the latent heat removed, and we know its formula is m dot times the latent heat H, or basically we can write this thing in LH, and m dot we have calculated as 420 kg per hour times latent heat, it is 109.3 kilojoule per kg. So basically this is, so we'll get the value of QL dot as nearly 45,906 kilojoule per hour. So the total heat removed, that is Q of total, it will be equals to this one plus this one. So this is 49,224 kilojoule per hour plus 45,906 kilojoule per hour. So we're going to add this and we'll get the value as 95,130 kilojoule per hour. So in the end we can conclude that the rate of heat removed from the bread, it is equals to 95,130 kilojoule per hour. So this was the solution for the A part. Next, in the B part, we have to calculate the volume flow rate of air in meter cube per hour if the temperature of the air is not to exceed 8 degrees Celsius. This is a condition given. Now in the B part of the problem, we are given that the temperature of the air should not increase by 8 degrees Celsius. So that is the delta T of air we can assume to be equal to 8 degrees Celsius. Now we know that the all heat released by the bread, it will be absorbed by the refrigerated air. So we can say that Q dot of T, it will be equals to Q dot of air. Basically here we have to calculate the volume flow rate of air, but before calculating the volume flow rate of air, we have to calculate the mass flow rate of air. So Q dot of E we are already obtained to be as this, and mass, this Q dot of air, it will be equals to mass flow rate of air times the specific heat of air times delta T of air, and this is Q dot of T. From here, the mass flow rate of air, it will be equals to Q dot of T divided by this term. So Q dot of T we have calculated as 95,130 kilojoule per hour divided by Cp, and the specific heat of air, it is 1 kilojoule per kg degree Celsius times the change in temperature we are given as 8 degrees Celsius. So we're going to solve this, and from here we'll get the mass flow rate of air as approximately 11,891 kg per hour. So this was the mass flow rate of air. Next we will be calculating the density of air. So density of air, we know it is P divided by RT, where P is the pressure, R is the universal gas constant, and T is the temperature of air. So pressure is the atmospheric temperature, atmospheric pressure, which is 101.3 kilopascal, divided by R, it is given as R, we know for air it is 0.287 kilopascal meter cube by kg Kelvin, times temperature we are given as minus 30 degrees Celsius, and if we convert this thing into Kelvin, we have to add 273 to it. So from here we'll get the density as approximately 1.453 kg per meter cube. Now next we'll be calculating the volume flow rate of air, and it will be equals to mass flow rate of air divided by density. So density we have calculated as 1.453 kg per meter cube, and mass flow rate of air, it is 11,891 kg per hour. So from here we'll get the volume flow rate of air as 8,185 meter cube per hour. So in the end we can conclude that the volume flow rate of air, it will be equals to 8,185 meter cube per hour. Now next we'll be solving the C part, where we have to calculate the size of the compressor of the refrigeration system in kilowatt. That means they are asking the power input to the refrigeration system, and we are given that the COP of a refrigeration system is 1.2. So in the C part, COP we are given as 1.2. So the power input to the refrigeration system, it will be equals to the Q of a refrigeration system divided by the COP. So Q of refrigeration is nothing but Q total, that is 95,130 kilojoule per hour, divided by COP we are given as 1.2. From here the power input, it will be equals to 79,275 kilojoule per hour. So this is the power input. Now if we convert this thing into kilowatt, we're going to divide it with 3600. So we'll get the approximate value as 22.02 kilowatt. So this is the power input, or basically the size of the compressor. So I hope you got the problem. Thank you.